For this GCSE chemistry required practical, we will be using titration to investigate reacting volumes. More specifically, we will be looking at the volume of 1 molar hydrochloric acid needed to react fully with 25 cm cubed of sodium hydroxide, and using that to work out the concentration of the sodium hydroxide. As such, you will need the following equipment: eye protection, a clamp stand and 50 cm cube burette, a small funnel, 1 molar hydrochloric acid, a 250 cm cube beaker, a 25 cm cubed measuring cylinder, sodium hydroxide of unknown concentration, 4 250 cm cubed conical flasks, phenolphthalein indicator, and finally a white tile. Before we begin, you will need to draw a results table similar to this. Firstly, close the tap on the burette and use both hands to move the clamp stand and burette to the floor, because it is not safe to pour acid at head height. Place the funnel in the top of the burette and fill with acid to just above the 0 mark. Remove the funnel and use both hands to return the clamp stand and burette to the desk. Place the empty beaker under the burette and open the tap until the acid in the burette has fallen to the 0 mark, or somewhere just below. Remember, to read the scale accurately, eyes must be level with the surface of the liquid, and you must read the scale at the bottom of the curve or meniscus. For example, here it shows 0.5 cm cubed. Use the measuring cylinder to accurately measure out 25 cm cubed of sodium hydroxide and pour it into a conical flask. Make sure to get every last drop and to aim for the bottom of the conical flask. Add 2 to 3 drops of phenolphthalein to the conical flask and swirl to mix thoroughly. It should turn pink because the sodium hydroxide in the conical flask is an alkali. Place the conical flask containing sodium hydroxide and phenolphthalein on the white tile under the burette. Before starting the first or rough titration, look at the initial burette reading. Here it reads 0.5 cm cubed. Record this in the results table. Then open the tap on the burette and add a little acid to the conical flask at a time, swirling after each addition. Stop when the phenolphthalein indicator changes from pink to colourless. This is called the end point, because all of the alkali has reacted with acid and the solution is now neutral. Look at the final burette reading. Here it is 5.8 cm cubed. Then record in the results table. Subtract the initial reading from the final burette reading to calculate the rough volume of acid needed to reach the end point. Here it is 5.3 cm cubed. So next time we will know the end point is close when we have added nearly 5 cm cubed to the flask. A second, more accurate titration will be carried out, but first look at the initial burette reading. Here it reads 5.8 cm cubed. Record this in the results table. For the second, more accurate titration, start as before. However, as you get near to the end point, add the acid a single drop at a time and constantly swirl the flask. Be ready to stop the instant a single drop causes the colour to change. Look at the final burette reading. Here it is 10.8 cm cubed. Then record in the results table. Subtract the initial reading from the final burette reading to calculate the volume of acid that was needed to reach the end point. Here it is 5 cm cubed. The volume of acid that was added to the flask is also known as a titer. Further accurate titrations can now be carried out. repeating until there are two titers within 0.1 centimeters cubed of each other. That is to say, they are concordant. Mark the concordant titers and use them to calculate the mean titer. Here they are the same, therefore the mean is still 5 centimeters cubed. We can now calculate the number of moles of hydrochloric acid in the mean titer by substituting our figures into this formula. The acid had a concentration of 1 mole per decimeter cubed, and 5 centimeters cubed of that acid were needed to neutralize the alkali, so the number of moles of hydrochloric acid in the mean titer was 0.005. From the balanced chemical equation, we can see that 1 molecule of hydrochloric acid reacts with 1 molecule of sodium hydroxide, a ratio of 1 to 1. So if we added 0.005 moles of hydrochloric acid, there must have been 0.005 moles of sodium hydroxide in the conical flask. If we rearrange this formula and substitute in the information we have about the sodium hydroxide, we can calculate its concentration. We had 25 centimeters cubed of sodium hydroxide in the conical flask, and have just worked out there were 0.005 moles of sodium hydroxide, so the concentration is 0.2 moles per decimeter cubed. Using the periodic table, we can calculate the relative formula mass of sodium hydroxide. We need to add together the relative atomic mass of sodium, which is 23, oxygen, which is 16, and hydrogen, which is 1. This gives us a relative formula mass for sodium hydroxide of 40. We can now use this formula and substitute the information we have to calculate the concentration of sodium hydroxide in grams per decimeter cubed. We know the concentration in moles per decimeter cubed is 0.2, and the relative formula mass is 40, so the sodium hydroxide has a concentration of 8 grams per decimeter cubed. Accuracy of the titration can be improved in a number of ways. Firstly, by washing out the burette before use, first with distilled water, then the acid to be used in the titration. Accuracy can also be improved by using a volumetric pipette to measure out the alkali, instead of a measuring cylinder. Methyl orange can also be used as an indicator for titrations. It changes from yellow to red at the end point.